Hey boys, so in 11.2 we're going to work with simplifying radical expressions. So if you have a radical, okay, you could break it down into, basically simplify it is what we call it, by breaking it down into two factors where one of them ends up being a perfect square. So for example, if a was 4, then we know that square root of 4 here is actually 2. So then you could break down a radical further to 2 root whatever b is. Okay, obviously that's difficult to see in variables. I'll show you some more examples that are going to help us out here. This quotient property of radicals is going to help us to work with fractions. So we already talked about this once before, but if you take the square root of a big fraction, okay, you could split it up to the square root of the numerator divided by the square root of the denominator. And the reason that's going to be helpful is because we need to rationalize the denominator. Okay, so we can't leave a square root in the denominator. So instead, what we're going to do is we're going to come up with a way of getting that square root out of the denominator. Okay, and basically what we're going to do, kind of a hint for later, is you're going to multiply both the top and the bottom by the square root of the bottom. Okay, so if we multiply by square root of b over square root of b, well, this is just 1. So it's not actually changing my number at all. Okay, it's just writing in a different form. Okay, so square root of a times square root of b, just from this product property up at the top, is just going to be square root of ab. And on bottom, if you have square root of b times square root of b, that's square root of b squared. Well, square root of b squared, the squared and the square root cancel each other out, so we have square root of ab over b. Okay, so this right here is the exact same thing as this. It's just written in a different way. Right, that's called rationalizing the denominator. Once again, difficult to see with variables. It'll be easier when we have some numbers in there. And lastly, how to add and subtract radicals. Right, you have to have the same exact number inside the radical in order to add or subtract. So a quick example of that, you can't do root 2 plus root 6. You can't do that because you have, they're not the same number. But you could do like 2 root 2 plus 6 root 2. Right, the way you do that is you just leave the radical, okay, pretending kind of like an x, and you just combine the coefficients. So 2 plus 6 is 8 root 2. Okay, it would look like that. Let's see some of this in action with some examples. Okay, so we're going to simplify something like this. This is going to be using the product property. Okay, so in order to do that, we're going to break this down. What you want to do is you want to break it down into two factors. Well, 48 could be broken down in a lot of different ways. Okay, you could factor basically 48. For example, 2 times 24 or 4 times 12, something like that. What we're looking for is perfect squares that are factors of that. Okay, so think about perfect squares. Right, the biggest perfect square that's less than 48 is 36. So you're going to start with asking yourself, does 36 go into this perfectly? So here's a list of the perfect squares. 1 squared is 1, 2 squared is 4, 3 squared equals 9, 4 squared equals 16, 5 squared equals 25, 6 squared equals 36, 7 squared equals 49. Okay, so I'm expecting that you guys know these perfect squares. Okay, so we're just going to go right down the list, see if any of these are factors of 48. 36 doesn't go into 48 evenly. 25 doesn't go into 48 evenly. 16 does go into 48 evenly. So you could break this down to square root of 16 times the square root of 3, because 16 times 3 equals 48. Okay, now square root of 16, we know what that is. Square root of 3, we don't know what that is. Okay, so square root of 16 we can rewrite as 4, because we know square root of 16 is 4. And the root 3, you just leave as root 3. So square root of 48 and 4 times the square root of 3 are the exact same thing. Okay, number 2, all right, this is the same idea. All right, you could split this up to square root of 25 times the square root of x to the 5th. Okay? Now, square root of 25 we already know is 5, so we don't need to worry about that. Now, square root of x to the 5th. What square root means is it means you can basically pull out any groups of 2. Okay? So, if we have 5 x's on the inside, you could pull out 2 groups of 2 out of there. Okay? So, we're going to rewrite this x to the 5th really quickly as x times x times x times x times x. Okay? Now, every group of 2 of something you can pull out of a square root because you pretend like there's a 2 on the outside. Okay? So you pull out groups of 2. So we can pull out 1, 2 groups of x's. So that's why you have x squared on the outside. and you're left with 1x on the inside, so root x. Okay, I know that one's tougher to see, but hopefully will help you see that better in the next couple examples. All right, and number 3, we've got 3 square root of b times square root of 2b cubed. Okay, so you multiply the coefficients together. There's no coefficient in front of the second one, so it's just 1. So 3 times 1 is 3. And then multiply whatever's on the inside of the square root together. Well, b times 2b cubed is 2b to the 4th. You've got 4 b's on the inside there. All right, so remember, 4b to the 4th, you could pull out any groups of 2 of something. So we've got 4 b's in there. Okay. Can't do anything with that 2 because it's just by itself and there's no perfect squares involved. But you could bring 2 groups of 2b's out. Okay, so you're bringing 2 groups of b's out, so you have 3b squared, and you're left with just a root 2 inside the radical. Okay, and number 4, okay, we can actually multiply the coefficients, so 10, and multiply on the inside m cubed n squared. Okay, so with this, we've got 3 m's on the inside, so how many groups of 2 m's can you pull out? Well, you could pull out 1 group of 2, okay, and you'd be left with 1 m on the inside, okay, because you pulled 2 of the m's out for here, and there's 1 left on the inside. And for the n's, you could bring 1 out, 1 group of 2 out, and you'd be left with nothing on the inside. So 10mn square root of m would be your final answer. Now some more examples here, working with the rationalizing, okay, here on number 5, okay, remember we can split this up by the quotient property, split this up to square root of 5 over square root of 49, and we can just simplify as much as we can. Well, square root of 5 you can't do anything with, but square root of 49 we know is 7. So the answer to this is square root of 5 over 7. Same idea for number 6, square root of 11 over square root of d to the 4th. Okay, so square root of 11 you can't do anything with, but square root of d to the 4th, you can pull out as many groups of 2d's as there are in there. Well, there's 2 groups of 2d's in there, so it's just d squared, and there's no d's left on the inside of the root. So you're finished. Now, number 7. Okay, on this one, you can't do anything with square root of 6. Okay, we don't know what square root of 6 is. So we have to do what we call rationalize the denominator. Okay, so to rationalize the denominator, you have to multiply the whole thing by 1. Okay, but 1 has many different forms. Anything over itself is equal to 1. So we're going to multiply this by root 6 over root 6. You always multiply by the square root of, or basically you multiply the denominator by itself. Okay, both top and bottom. So on top we've got just 7 times the square root of 6. And on bottom we got square root of 6 times square root of 6. Well, square root of 6 times square root of 6 is square root of 36, which we know is 6. So this works out every single time. Right? When you multiply by itself, the radicals just go away and you're left with whatever that number is. Okay, so very, very similar. Here in number 8, right, square root of 3 you can't do anything with, square root of 5a you can't do anything with. So if we multiply top and bottom by square root of 5a over square root of 5a, okay, what we do is we've got on top, you multiply 3 times 5a is square root of 15a, right, 3 times 5 is 15, and on bottom the radicals go away and you're just left with a 5a, and that's all you have to do. Okay, now in 9 through 12 we're going to be doing some adding and subtracting. Okay, so remember what I said, you can only combine things that have the same radical, or same radicand, same number underneath the radical. Okay, it's very similar to combining like terms. Okay, so you see we've got quote unquote like terms, right, with the square root of 14s. Okay, so you can actually combine those. We do 7 minus 4 is 3 root 14, and the root 21 you just keep by itself. Okay, so it's really, really similar to adding like x squareds and y's and y squareds and y cubes and all that stuff. Okay, for number 10, okay, so another thing you could do here is you might be able to manipulate these radicals, simplify them like we did with square root of 48 back in problem number 1. in order to make them have the same number underneath the radical. Okay, so that's going to be really useful. So 28 we know is the same as, let's write it down here. All right, 28 is the same as square root of 4 times square root of 7. Well, square root of 4 we know is 2, so it's the same as 2 root 7. Okay, so because we know square root of 4 is 2, right? We don't know what square root of 7 is, so that's why we have to leave it like that. So we could rewrite this problem 2 root 7 plus another 2 root 7, because square root of 28 is the same as 2 root 7. So they have the same number inside the radical, so you could just add the coefficients. 4 root 7 is the final answer. Okay, all the properties still exist for this. Okay, so for multiplying just this monomial times the binomial, you could still just distribute the square root of 3 in there. All right, so 2 times square root of 3, you don't have to do anything with that because one's a root and the other one's not, so it's just 2 root 3. And root 3 times root 12, you just multiply the numbers and keep them on the inside of the square root. It's root 36. So you try to simplify this as much as you can. Well, we know that square root of 36 is 6, so 2 root 3 plus 6. Okay, and the last problem here, number 12. Number 12, okay, you still have to FOIL. Okay, we're multiplying a binomial times a binomial, so we've got root 2 times root 2. Well, remember what I said, if you multiply two things together, right, if they're the exact same, the roots are the exact same, they could just cancel out. Okay, and so it's just the number that's left. Another way to think of it is root 2 times root 2 is root 4, and root 4 is 2. Okay, now the outside, root 2 times negative 3 root 5 is just a minus 3, right, because 3 times, pretend you got a 1 here, negative 3 times 1 is negative 3, and root 5 times root 2 is root 10. Now the insides, root 5 times root 2 is just root 10. And the last, we've got minus 3 root 25. Okay, now the only thing that we could do here to simplify is combine our like terms here, and we have root 5 is the same as 5. Okay, so this is the same as 3 times 5. Okay, so right here, we really have a 15, right, because 3 times 5 is 15. So we can combine these like terms as well. Okay, so we have 2 minus 15, 2 here, minus 15 here, it's negative 13, and negative 3 root 10 plus 1 root 10 is minus 2 root 10. So that would be the final answer for that one. That's simplifying radicals. I'll see you guys in class.